I think permission has given Ankit. Hope everything is fine. Ankit, you there? You can share your slide, title slide. Indrani?
Hello.
You can share your slide, title
I
slide.
think I think there is a exchange of the tutorial. I think Vivek
Okay.
will show first, then
Oh, so Vivek is presenting first, huh?
yeah.
Okay. Okay then, Vivek.
Yeah, yeah. So I have. I'll share it now. Okay.
Yeah, okay.
So before that, like, so okay. Anyway, let's wait for 2:30 and then maybe we'll start because students have to actually go to the IIA tutorial. I mean, the IIA summer school page and then download the. There are two handouts there for today. Please download that and then keep it. I mean, these are the instructions for the hands-on. Sorry. Is this visible?
Yeah. Yeah, it's fine.
So let me know like when to start. Like how many students are there now?
143, but it's okay. We can go with time.
Okay. Should we wait for 1 minute? Okay, we'll
Okay.
start at 2:32. Like let them.
Yeah.
If more people are joining, let. Uh, okay, so we'll start at 2:32. So so all of you who have already joined. So first we will do the galaxy morphology and color magnitude diagrams of the galaxies. So there is instructions given at the IA summer school web page. I mean, in the tutorials tab, like you go there and then there are two handouts or maybe PDF files uploaded there. So please download them and then keep it in your, I mean, desktop or laptop. I mean, these are the instructions for the hands-on, and yeah, basically have to go read and then Okay, so I think we can start. So this is the PDF file. I'm displaying it here. You can see that, and the basic idea is like we'll first do this, see several galaxies and see what are their morphologies. This you learned in Moshmi's class. So when you learned that there are several types of galaxy morphology, and then you also learned about the color magnitude diagram of galaxies. There is a red sequence, there is a blue cloud, and then there is a connecting green valley and all. So we're trying to, using some data, we'll see like the different galaxy morphology. We'll familiarize with the different galaxy morphologies and then try to make a color magnitude diagram of galaxies. So what we are trying to do is basically take the data from this called Slow and Digital Sky Survey, and this is I have another presentation, like I'll briefly discuss about like what are this and then how this is done. And then there is another effort which is called Galaxy Zoo. This is a citizen science project where the citizens kind of classify these galaxies into different morphological classes. By visual inspection, looking at the images of the galaxies. This is probably many of you are already aware of this and are also part of this, but this is Galaxy Zoo. So we'll take the morphological classifications from Galaxy Zoo, but mainly look at the SDSS galaxies. And then you can, for the details of SDSS and galaxies, you can go to these links. Then we'll use, SDSS is like a big database. It has lots of, it has a lot of data. So then you basically have to talk to this database using a programming called like SQL, which is called structured query language. It's very simple. It's not very detailed. So you basically use SQL commands to query and then generate a table of different type of morphological classes. This is the code. Then you have to basically select this, and then this is the link which is given here. So this is the SQL query page for the SDSS database. Click on this and then you copy and paste. And but you have to understand this. But then I have a slide. I'll tell you what. So there is a brief explanation that I've given here for each of these commands, and you can read this and then understand. And so then what you have to do is you have to basically run this query and generate. So, okay, before that, I want to actually start another presentation where I'll briefly tell about the SDSS and galaxies too. So I'll just stop this and then start another presentation. Yeah. Okay, so is this visible?
Yes.
Yeah. So we are basically taking data from Slow and Digital Sky Survey, which is called SDSS, which is basically the goal of this project. It's a big collaborative project, like where there are like several institutions involved. Like, for example, 26 institutions. There are associate members. There are several participation groups, and also it's an international collaboration, which basically aims to create the most detailed map, 3D map of the accessible sky to this. Using a 2.5 meter telescope in US. New Mexico in US. So basically, for three-dimensional map, you need the locations like XY coordinate, which is on the sky, which is basically called the array and deck. I think like you must be familiar by now, the array, what is an array and what is a deck. And then the third dimension, of course, is the redshift, like how far is this? So it's trying to create the 3D map of the universe using these images, as well as redshift you can only know by you can only know by knowing by taking the spectra. So this is a big project, and so there's huge amount of data available with this, because and it's a novel technique by which it takes it's called multi-object spectroscopy, and it takes around 10,000 spectra per night, as compared to the normal conventional spectroscopy. You'll hardly get like 5 to 10 spectra per night. So it's a novel thing, and then this has kind of revolutionized the way astronomy is done, because like now astronomy is not a data limited science. it has become a data-driven science, like where lots and lots of data are available. So basically, and the one good thing about this SDS is that they have yearly data releases. They make the data public, so anybody can go and download these data and use for their science. And then second, so we'll basically use the data from the SDSS. And they have a nice website also, so you can go and check what is SDSS and all. The second thing is like Galaxy Zoo, which basically aims to use the citizen science, resources from the citizens to classify different problems, not only in astronomy, but in many other fields. In astronomy, what happens is like they take the SDSS images and then display it to the people who have volunteered to do this, and then they ask them to classify them according to its shape, like whether it is a clockwise spiral, anti-clockwise spiral, edge-on galaxy, or a spiral or elliptical galaxy. So this is like this will be displayed to you, and then you have to click on one of these buttons, like which is displayed here, and then many people do that, and they based on they create a probability out of this many votes, and then depending on the probability, they can calculate whether this is an elliptical galaxy or a spiral galaxy. Okay, and then the next thing, which probably it will be difficult for you, is the database part of the problem. So database is basically a systematic collection of data. And you arrange any data in a systematic way, it becomes a database. And there are several languages by which you can actually talk to the database. This is basically a set of commands. And then SQL is a standard language for querying, and maybe you can manipulate also the data. In the sense, if you have to change, you actually, all this information you load into a database, you can actually retrieve this from the database also. If you want to manipulate, you have changed some of the entries, you can also do using SQL. So what is a database? Data is, in a database, it's basically a relational database. Where data is basically stored in tables. Tables is basically two-dimensional array of, it's a columns and rows, with each columns will have some value, and there are several entries which are basically rows. Horizontal rows are individual data points or records, and then vertical columns are types of data columns. And for example, this is a database for a bank where there is customer IDs there and customer name, customers. So this is one table. This is the first one is one table. The second one is a table of the, which basically maps the customer ID to the account number. The third one is maps the account number to the balance. So suppose if I want to actually get the balance of some person, for example, Smith, if I have to basically know the balance. So I have three tables available here, and I have to join these three tables by using some indices. Basically, the tables are related by index. For example, this first two tables are joined by some index called the customer ID. So once I know the customer, there's a unique customer ID for each entries. Then once you map the customer IDs, you basically know what is the account number of Smith, and then this second and third table is joined by the indices, which is the account number. And then once you join this, you basically know what is the account balance of Smith. So this is basically how a database works. There are, it's stored in tables. There are several tables, and these tables are joined by some indices. Okay, just understand that. And in SDSS Sky Server, there are several tables. For example, for photometry, it's a table. Galaxy itself is a table. So it will have all the photometric magnitudes of galaxies, and then all the related parameters to the photometry and the galaxy will be the parameters of each table. For example, here, I don't know, yeah. So here I show a flowchart of two different tables. One is photo object all, which is a photometry of all objects in SDSS. Then the second table is spectral object all. And for each of this, there are several parameters associated with these tables, which are basically what are the different columns. For example, it will have run, I think Redshift is there, photo, then magnitudes is there, photometric redshift is there, all this. And for spectroscopy also, like there are several columns associated with them. Okay. Yeah. So how do you know these things exist? So there is something called schema. So schema is basically the logical arrangement of all the information in the database. And in SDSS, there is something called the Schema Browser. And there is a web page. I've given the web page here. I mean, you will see this when you do this hands-on. Like there will be something called Schema Browser. You will notice, and you click on that, and then you'll go to this table. You can search for, if you know the table, what table you are looking for. You can just type it here and go, and then it will list matching that what you have queried for, and then it will have all the descriptions. So if you are in doubt about a particular table, whether it has the relevant column or not, you basically have to go to the Schema Browser and just do that. And then this is this structured query language. It's the standard language for manipulating and querying data. So it basically it's very easy. Like it has 3 blocks, and so there's a select, and then there is a from, and there is a where. The select basically tells you, the database, which columns of the data you want it to return. For example, I want to return array and deck. So you will basically say select array deck, and then from where? From where means from which table you are querying. For example, if I say like spec object all, so you have to say like from spec object all. Then where basically gives you the constraints. Like, I mean, for example, I want only array between 140 and 141, and then deck between 20 and 21. This is a constraint, right? So this will only list rows which are which satisfy this constraints. So these are the 3 things, and we'll go back to the SQL, and then maybe I'll explain it there. And then so I just want to advertise about this nice resource that you have. Like this is like the SDSS Sky server. You should go and explore this, and there are several projects also you can do. I mean, these are the data access tools, and then on the side you can have for education, and then there are projects also available. I mean, using the SDSS data, so you can just try to do this yourself, just if you are interested. Yeah, and another resource is the Sci server. This is a science platform which is provided by the SDSS, and I mean it gives you storage spaces. It can host you like Jupyter notebooks, and it has a hosted data set. You don't have to actually store this data in your computer. So once you log into the Sci server, you create a login in Sci server, and then once you log in, then you have all these resources available. For example, a lot of data sets available, and then you can just directly run maybe your Python Jupyter notebooks and all there. So go and explore Sci server as well. The link is there. But anyway, so I'll stop this and maybe get back to the so for people who think they're confident to start, they can start actually. And is this visible? Like the hello?
Yeah, it is visible.
Yeah, so let's actually dissect the SQL query. So I've already told you what are the basic 3 commands in SQL. So first one is select. And then I'm only limiting it to top 10 because, I mean, otherwise it has millions of galaxies, and it will start listing all of them, and it will be a mess. Okay, so I'm limiting it to only 10 entries. So that's what is specified by this top 10. And then these are the parameters I am querying. Okay, but you should I mean, you'll notice that, I mean, there is something appended, g dot object id, zns dot envot. I mean, it's not as simple as array or deck that I showed previously. That was just a very simple SQL query. So this basically tells you like, so this parameter basically comes from g, which is defined here as from the galaxy table. Okay. Okay, these are the parameters, and before the dot, there is some characters which basically denotes the table from which this parameter is coming. Okay, so these are the parameters I am querying. So there's object ID. Then this is the Galaxy Zoo table I am joining. So here, from first I select it from Galaxy as G, and then I join the Galaxy Zoo, I mean, the Galaxy and the Galaxy Zoo, which is basically defined by Zoo no spec. I mean, these are like things in Galaxy Zoo with no spectra available. So this is, so I call this as ZNS. Then, so I have to specify some index, right? Only then it will join. So then I say, okay, galaxy.objectID is ZNS.objectID. This is the index which basically it will match. Again, I need some other information also. This is like from the Galaxy Zoo, I'll take the morphological classifications or the probability of the morphological classifications. And then there is another table called photo tag, which basically has the photometric parameters, which you will need for plotting the color magnitude diagram. So I take this photo tag as P, and then again using the object ID, I match it. So this P will come here as P dot magnitude, or model mag U as U magnitude. Model. So there are 5 pass bands in SDSS, that is U, G, R, I, Z. So these are the 5 magnitudes it's returning. Then it will also P dot object ID. And for demonstration, which will not actually use the redshift, but this is S dot Z as redshift, but like then I am joining the spec obj table, and then this is the indices on which it will be joined. And then finally, there is a photo Z table where it will have the absolute magnitudes, because like if you have to compute the absolute magnitude, you need to know the redshift of the source. And then this photo Z table has the photometric redshifts, so it will give you so the absolute magnitudes. The photo Z as PZ on G dot object ID is equal to PZ. So, and then I give the constraints. What are the constraints? G dot clean equal to 1, which means I need clean photometry. This is from the Galaxy table. So I want to specify it's a clean. I mean, I don't want any artifacts in my photometry. Then ZNS.nVote is greater than or equal to 10. Means like the number of votes in Galaxy should be greater than or equal to 10. So at least 10 people would have classified it. Otherwise, like I don't trust it. Then I give something called ZNS.p.edge, which basically is the probability of it being an edge on Galaxy. You can actually give it 9. So I should have given it 9. So then it will give you only the cleanest this thing. And yeah. And what are the parameters I am querying? So these are the parameters. First one is, okay, it comes from the Galaxy. This is the object ID. Then number of votes. It will display the number of votes. Then the probability of it being an elliptical. This is ZNS.p_el. Then probability of it being a spiral clockwise. It will be p under clockwise, and then anti-clockwise. Then edge on. And there is something called don't know, which people classified it as don't know. Then there is a merger probability. Then this comes from the photometry, like photo tag, RA, deck, run, rerun, camcall. These are, then type is also there. Then magnitudes, U, G, R, I, Z, object ID, redshift. Then the PZ I am querying from the absolute magnitude, PZ.absolute magnitude, absolute magnitude G, absolute magnitude R. So once you have to copy this and then run it in this link. Okay, I have explained to you, and then it will generate a list of. So yeah, I've changed it to 0.9. Please use 0.9 because in the handout I think I've given it as 0.7, but it's okay. Like 0.7 will also work, but some dubious cases might come. So once you, for example, first thing is you run it with, suppose, edge on, and then it will list all the galaxies with edge on probability greater than 0.9. Then you have to basically copy the object ID of this. So the first column will be your object ID. Copy this, go to this link where it will display the images. Click on this link, and there is a search. So if you click on this, can you see this web page? No, right?
No, we can't see it.
Okay, so if it will go to something like, yeah, this page.
No, if you are,
Yeah, it's visible.
Yeah, this page, and then you copy this object ID and then paste it here and hit go, and then you will have the image of the queried object here, and then you can click on this and then maybe play around with the with this. So then the first thing that you will do is, I don't know, I had, yeah, this is the query. I think if I submit, so you have to, this is the link I earlier shared, and then you have to copy this. I don't know whether this will work. And so it will generate something like this, 10 IDs. Then the first one is the object ID, is the number of vote. Then this is the probability of it being an elliptical, spiral anti-clockwise, edge on. So basically I have given Z edge greater than 0.7. So you notice like all these are edge on galaxies. So then you have all the parameters. These will be required for the color magnitude diagram. So what you have to do is like you have to copy this, and then I don't know. So I showed the. I clicked on the one. Sorry. Yeah, I'm just reopening it. Then I'll copy it here. So I'm querying for an edge-on galaxy, and this, see, like you have a edge-on galaxy. Okay, so you do this, you generate the list for different classes, morphological classes, and see like how they look. You can display maybe, I don't know how many you want. You can display like check, and then that's the first part of the exercise. You will basically get familiarized with the different morphological, how they actually look in data. And the second part is basically, I have to share again. Yeah. Okay, that's the first part. And then the second part is plot the galaxy color magnitude diagram. So you'll use the basically, this query has all the relevant things there, like because we are querying the all the magnitudes and the absolute magnitudes, which will be required for your color magnitude diagram. So basically you'll run this for 100 ellipticals and 100 spirals clockwise. Okay, so what it means is that you have to basically change the probability here. You have to give it as underscore p underscore edge. You have to change it as p underscore el, and then maybe select top 100 to actually change, I mean, return 100 rows, and then generate a table for the ellipticals and generate a table for the spirals clockwise, and then use this table and to, I mean, you can choose whatever plotting software you want, like Python, GNUplot, I mean, even Excel, if you can import this into these two tables in Excel, whatever you have, like do that, and then like plot this absolute magnitude R versus, you have to compute the G minus R, G mag minus R mag, then plot that, and then there is another version of it, which is absolute magnitude of U minus absolute magnitude of R. So, and in this, what you clearly notice is the segregation of this blue is spiral galaxies and the red is the elliptical galaxies, and there are several caveats here. It's not similar exactly. So you have seen the CMD in the morning lecture. So there is a clear sequence and there is a blue, but then it's not exactly similar to the CMD that's seen in the literature. But there are reasons, because it's like, of course, it's not, I mean, we are only taking the galaxy zoo classifications, and I mean, there are only 750 spirals here, and so it's not a homogeneous sample, and there is no dust correction applied, and these are nearby sources, so sometimes the photometry can be bad. And yeah, but then notice the difference in the, I mean, how these two are clearly separated. That's the one thing, and then you can have some suggestions for how you can explore more. Yeah, so now you're free to actually do this. So I think I have explained it. If you have any doubts? So is it okay? You guys?
Yeah, I think it's okay. So let the students do the things, and then.
Yeah. So first part you will do this, and then at the next sessions we'll do the rotational curve. And so we'll be here, and if you have any.
I think there may be a few questions in the chat box. I think you can just answer them in this chat box.
So can you explain the graph part again? So you have the two tables. Okay. I didn't actually explain how to download the data. So I'll just do that now. So share screen. Yeah. So this is here is where you will paste it. So when you click on HTML, it will give you a HTML table, like when it will open in a new this thing. But then if you click on maybe XML or CSV format, or even I don't know whether you're familiar with Fix or not. But then you click on this, it will allow you to actually download this. It basically that file is downloaded as a CSV file. That can be imported into I mean, maybe if you are using Python, if you're familiar with Python, then just read this file. It will have all the magnitudes for ellipticals, 100 ellipticals. Then you plot G minus R versus absolute magnitude of R versus G minus R. Then you get the color magnitude diagram. I mean, then on top of it, then you have to also do the exercise, like you have to download for spirals clockwise, and then plot both of them in two different colors, and you can see that they are separated. So, and then I think how to get, so yeah, I think how to get file console, I think I've answered that. Do we have to log in first? No, you don't have to log in. Login is not okay. Okay, so can you show one example by doing it? I'll not plot because I've given already the plots there. That you have to do. So this is basically the query. I've copied and so already there will be some query. You have to clear that and then paste the query that is given in the PDF. Yeah, so I'll probably do 9 and then click on this thing and then do it on. We will have this then. So if I can open it in some, yeah. So this is in these are the things. So you can basically, I mean, I basically do it in Python. Take a difference between this column and this column, and then plot this versus the difference. That's for the so this is edge on. So basically, you have to do it for ellipticals and spiral clockwise. So in the this thing you have to say, yeah, elliptical greater than 0.9. Sorry, I should first show you the HTML table. See, like now ellipticals all have greater than 0.9. All others are 0, of course. So These are clearly elliptical galaxies. Then for these elliptical galaxies, you take the difference, G minus R, and then plot. And then similarly do this exercise for spiral clockwise, and then, yeah. So is that good or? Okay. Yeah, first do the first part of it, like get familiarized with the different morphological classes. Then by then you will have the, I mean, you know what to do for the color magnitude diagram. So once you run this for 3-4 times, you know what's happening, and then you can easily do the second part. Indrani, is that okay?
Yes, sir. I think it's okay.
So I'll be here. If there is any doubt, please ask me. Like I try to answer.
Okay. Okay, sir.
I'll
Fine.
keep on mute. So is the code working, or did you try? I mean, I see no response at all. So is it working or? Okay, it's working. Okay, yeah, then you proceed.
वो देना तो शायद
So how is this going? Like, is everything okay? Can somebody confirm? Or we don't have any response from you, so we don't know what you're doing. I see no response. So not able to do the color plotting. So, so what are you using, Gopal? Are you using?
So I'm using Python.
Okay, so what is the error that you're getting?
Sir, we need to import the file, right? That actually I'm not able to do it.
So what command are you using? So there is, it's a CSV file. Do you know pandas? So I'll just type the import as PD. Then suppose I'll wait pd.csv. In quotes, you give the file name. Okay, that will read the file. So you can just do df.head. Will give you the information, and then all the then df dot keys will give you what are the column names. And then basically use matplotlib. You know how to use matplotlib?
Yes, sir.
Okay. So is this helpful, or you'll manage from here?
I'll manage it from here, sir. Thank you.
Okay. So there is a question from YouTube, like, is it the same analysis methods used for research purposes? Yes, it's almost same, but like this is a basic version of it. But like then you'll add many more complexities to it. But it's done using SQL queries only. But then the particular, like the web page that I've given you doesn't allow you to run a large scale SQL query commands. It times out with the number of rows, and then there is a timeout. I mean, if the query takes more longer, it basically times out, so it will not allow you to. So this is a basic SQL kind of a wrapper. Then if you want to do it for research and all, like there is something called CAS jobs, which is again provided by SDSS. Then you go there, create a login, and then you write your SQL query there. So it's a big server is it's sitting somewhere, and then this will run your query. I mean, it will basically keep it on queue because many people will be trying to access this server. And then once your time comes, your SQL query will run, and then it will give you output. So then it will also mail you that your output is ready, and you go log in again and then download the output. That's basically how research is done. Yeah, so this was a question from YouTube. So yeah, so load text. So Vinayak is asking, I read this file using load text command, but yeah, because object ID problem, there is this format issues. Yeah, format issues. I mean, you have to specify with load. I mean, I think gen from text will work better, but load text has issues. It will not work on CSV. Yeah, okay. So I mean, better is to use like pandas. It's very easy to read in a CSV files. Yeah. And also remember that, I mean, you probably will not get the exact picture which is given in the PDF, because that's done using 2000 ellipticals and around 750 spirals. I mean, I limited the number to only 100 in your PDF because otherwise it's a bit too thick. But you can try with 2000 and I mean, you can increase that number that I have given as a. Is it okay to use Excel? Yes. If you know Excel, you can use it. But then the problem is you have to append two files. I mean, basically plot. First, you have to take the ellipticals, and then then import the spirals, and then basically join these two. I mean, tables one after the other. Then you do the difference between G minus R color, and then basically plot. Then Excel has that small thing, but then if you know how to append it, then it should work. So there's another question from YouTube. Hamish Dalwari. So he's asking like Origin 2018 or Sigma plot. Any plotting software you take it, like you just basically have to read two files, take a difference between two columns, plot another column against that newly created column. So any plotting device should work.
Indrani, you there?
Yes, I'm here. Tell me.
Okay.
Yeah.
Hello, I think we have reached the time limit, so it's 3:30 already.
So let them continue, right? Because there is another session and then there is also group photo, I think.
Yeah.
3:44. So you don't have to stop this, right?
No, I don't think so. I think everyone will join here only.
Yeah, okay, let it continue. Probably, I mean, this is now a break from 3:30 to 4. People who want to continue can continue because we will start the next tutorial at 4 o'clock. So there are some questions. Any idea to how to plot CSV file in Excel? So basically I have to import this CSV file into Excel and then basically say, so there is a delimiter there where CSV is comma separated variable. So you have to say that it's a comma, which is the separation between two columns, and then choose that comma, and then it'll displayed as, it will be displayed properly. Then again another file, and then have to append these two, maybe copy paste and then plot. So group photo, is at I mean the rostered to 345, and we'll take a photo at around 350, I think. Yeah, I don't know. So actually import, can you tell how to import CSV? Oh, so I've given the commands earlier. So somewhere, I mean, go somewhere. Yeah. There are some. Oh, these commands are probably only. Doesn't. Oh, sorry. Like this, these commands are actually, I think, only went to, I think, Intra. Yeah. Okay. Yeah. Okay. Follow what is Ankit is typing. Just ignore my message. Ankit is typing. Just follow what he's doing.
Vivek, can't you show up screen and doing something to display?
For what? For plotting. Are you telling about plotting, Crispin? Okay, so do you want me to type the commands somewhere like in a terminal and show you like how it's done till the next week? I mean, if many of you have problems, probably. Okay, I'll quickly do for one. Okay, so can you see my terminal?
Yeah, it's
I think, CD downloads, I think. Yeah, so I have these CSV files. So basically I'm trying to read one of them. So I'll go to IPython. So then do this import pandas as PD. Now then I define something as PD dot. So this is how I do. So there is another way. You can also use table.
Actually, it is not visible actually.
It's not visible.
I think
No,
the
I think.
screen is
No,
frozen.
no, screen is visible.
No, the thing he is telling is not visible.
Okay, okay. Okay.
Can anybody see? Crispin, can you see?
No, what you are writing is not visible.
Ah, okay, okay. So maybe is this fine?
Section with your which one?
Is this fine?
No, I guess.
Not yet.
No.
Ah, okay. I'm just zooming. Is this okay? Ah,
It is showing old screen actually.
sorry.
It's look
It
like
is,
your terminal.
yeah.
It's visible. I don't know. Is it now? I stopped. Like I'll just try to.
Yeah, it is stopped now.
Otherwise, instead of application share,
Okay, I'll do. Then I just wanted to plot. That's why I used the terminal. So this terminal is not visible, right?
No.
No, I think you stopped sharing.
No, no, that I stopped. Like so, I'll try
share
once
the
more.
window.
How about this? Something.
This is your IPython terminal, I guess, but it's what you were writing is not visible. I think you are not sharing the full window.
Okay, then what I'll do is I'll better type in the stuff here. I'll give here. So this is visible.
Yeah.
Yeah.
So maybe I'll do. Okay, so suppose like import. This is okay.
Yeah.
Yes, it's fine.
Okay, then I'll do something like this. Oh. This is okay. This is the file name. Are you able to read? Just tell me if it is not.
Yes, yes, yes. It's fine, fine. Okay.
Then df.head.
It's gone again, I think.
Okay, I'll just type the command. So basically, so then you basically difference you have to.
Is the tutorial over?
No, I don't.
Still, people are still doing, I think.
Nice. Crispin? Is Crispin around?
Yeah, yeah.
Ah, okay. So you will give us all directions how to do the photo, okay?
Oh, okay. Nothing. Everybody. Yeah, I'll take a screenshot. Everybody should on the video
Yeah. So we'll,
by 3:50, right? 3:50.
yeah, let's take the picture at 3:50. I asked the IIA people to
Oh,
log in at 3:45,
by 3:45. Oh, okay.
just to
Okay.
wait for people to gather. So 3:50 will take.
Yeah, yeah.
So I'll if stop sharing and maybe I'll copy this and maybe put in the chat box.
Vivek, you can keep it for another 5 minutes.
Okay. I've given it in the chat box, but anyway, I'll also display.
അതൊക്കെ മതി.
So okay, I see several IA people. Crispin,
Yes.
is it time for us to?
350, right? Yeah. So people have come, or shall we go increase?
Um, it's very hard to see if all of the IIA people are around. I do see
Yeah,
some
but
name.
I'm good, but I'll give another few minutes. Yeah.
Okay. So we'll keep
okay.
time. Crispin,
Anyway,
350
we could see
sharp.
the number.
We will turn on video when you
Okay.
instruct us.
Okay. Okay. Yeah. So, okay, then we can go for the photo screenshot. So please, I'm not forcing, but whoever can open the video, please, you can open it.
Okay.
Okay, I think it seems like number was increased and decreased. Okay, it's a last call. Please open the video and I'm going to take a screenshot.
You can take many pictures.
Okay. I think not many people not yet open. Okay, okay. Okay, otherwise I had to go for another setting option. 1 minute. Maybe we can collect only the video people. Sure.
Is it done, Crispin? I just need to leave to another meeting.
I think we can go.
If I leave, your frames will change.
Yeah.
It's dynamic, right? Because
No, I'm.
okay, I'll hang on for a few more minutes. Don't worry.
Yeah, thank you. Just 1 minute. It's okay, you can go ahead. I think many people didn't turn up, no problem. We'll go up with whatever it is.
Okay, so
Yeah, fine.
okay. So we can turn off the video now?
Yeah.
Yeah.
Okay.
Thank you. And
Thanks.
hope everything is going fine.
Yeah, I think so. I think it's going great.
Okay. All
A lot of
right.
excitement.
All right. Yeah. Thanks.
Bye. Okay, you can continue with your tutorial. Uh-oh. Yes, the photo will be shared with everybody. Many photos were taken, so Prachi, don't worry. I'm sure your picture was there in the previous one. Okay, attendance link, huh? So Crispin, we will share the attendance link at the end.
Which one?
Attendance.
Yeah, I mean YouTube. Yeah. Okay, right now I'll share share in the chat box. But it is advisable. People can close by 6, at least 6 o'clock. It's going on up to 7:30. Maybe people are sharing. I don't know. Timestamp is visible when you are signing attendance. Timestamp is easily visible for us, so you can keep in that mind.
Yeah. So don't join the meeting. Give attendance at 7 o'clock. That is embarrassing.
Yeah.
Okay, so I will also log out. I will leave you guys to the tutorial.
Hello, Indrani or Sujay, Ankit, any of you there?
Yeah.
Yes,
Yes,
yeah.
ma'am.
Okay, good. Then when it's 6 o'clock, yeah, now it's 4 o'clock. So shall I, do you want me to explain the slides to them? Bring it up? Because that's what I saw Vivek did.
Yeah, I think so.
Okay.
Yes, ma'am, I think.
Okay. Okay. So I'll just describe it very briefly and then you can all take over. If they have, anyone has any questions, let me share the screen first. So after, Indrani, after I explain things, I'm just going to be silent. I think you, Ankit and Sujay can take care because it's very small, the exercise that I've given them. Huh? Is that okay?
Yes, ma'am. No
Yeah.
problem.
Okay.
Yeah, fine.
Take. Okay, so someone is host here. I can't share right now. Who is the host? Prava, huh? I think Prava is
Let
the
me
host.
check. I think, no, I think Crispin.
It's me.
Yeah.
Okay.
Oh,
For the
Crispin.
event.
Okay. Crispin,
Yeah.
have you disabled it now? It says here when I try to
Okay.
share.
1 minute. Yeah. Yes. 1 minute. Sorry.
Yeah. No
Yeah.
problem.
You can check now.
Okay. Okay, I'll just share this. Right. Okay, so I'll just, I want to talk to all of you. I think all of you must be busy still with the SDSS problem, the tutorial that Vivek has been doing. But if you finish that, then you can do the exercise, the small exercise that I have done here, that I have presented here. So this tutorial exercise is about calculating the dynamical mass of a galaxy and then using the visible mass, which is the stellar mass, molecular hydrogen mass, and the neutral hydrogen mass, to calculate basically the dark matter content. So the slide that's here, and you all must have downloaded these slides from the website. If you haven't, please do so, okay? Because it's better to have it on hand. So what you have to do is taking the concept of galaxy rotation and the rotation curve which is shown here, you have to basically use the last radius of the rotation curve and the flat rotation velocity to calculate the dynamical mass. And what I've shown in the figure here is that for any galaxy, the rotation curve is basically made up of a contribution from the disk, which is the stellar disk, from the gas, and also from the dark matter halo. So it's very simple. You all know from the satellite problem that the dynamical mass is given by V squared R divided by G. So now if you take the last radius, okay, R, from the rotation curve and the flat velocity at that point V, then you can calculate the dynamical mass. And as you see from the relation below, dynamical mass is equals to m dm, which is the dark matter mass, plus stellar mass, plus neutral hydrogen, and plus the molecular hydrogen. So the dark matter mass is simply m dynamical minus all the baryonic mass, basically the sum of the stars and the gas. Now, once you've done that, and I've given a table for that, then the next thing that you have to do is just plot some quantities. Now, when you calculate, because I know you are all not used to the units of kiloparsecs, what I've done is I've given you a simplified formula. So m dynamical is equals to v flat squared into r flat into 2.25 into 10 to the power 5. This will give m dynamical in units of solar mass, m sun. Okay, and then all you have to do from the table is to subtract the sum of the baryonic mass, and that will give you the dark matter mass. Now, there are about 16 galaxies. You can do it by hand, the calculations, or you can write a small program and just calculate it very fast. Okay, so now here is the table. So from this table has various quantities, but what you have to take from this table is you have to take the rotation velocity as v flat. I've put my cursor here. I hope you can see it. So v flat column lists the flat rotation velocities. Okay, that is your v. Now, for the radius at which you get the flat rotation velocity, you have to go here on the side, and against each galaxy, I've given the distance. So for DDO 154, it's 2 kiloparsecs. For NGC 7793, it's 8 kiloparsec. Okay, so please take all the radius values from the column here in kiloparsec, take the velocity from this column here, the neutral hydrogen mass, and then the molecular hydrogen mass. Remember, these quantities, stellar mass and then the gas masses, are all in units of log to the base 10. So to get the actual value, you have to write them as 10 to the power, say 7.1, 10 to the power 8.7, like that. And for values where you have only upper limits, just take them to be 0. Because right now we have not been able to detect any molecular gas in those galaxies. Now, once you've done that, simply make 3 plots. The first plot is M dark matter divided by M dynamical. That will tell you what is the fraction of dark matter typically in galaxies, and does it vary over the galaxies a lot. So this is the first plot. M dark matter divided by M dynamical against the log of the stellar mass. The second is the star formation rate plotted along with the log stellar mass. The star formation rate is given in this column over here, solar mass per year. Just take that value. Now, the third plot, which is very useful, is the ratio of gas to variance. So it's basically the ratio of the MH1 plus MH2 divided by the total mass. That means the gas mass and the stellar mass. Okay, and on the so on the y-axis you plot that, and on the x-axis you can plot the stellar mass. So I think actually, rather than me saying all these things, just look at these plots. You should be able to reproduce them. And if you have any questions, you please ask Ankit or Indrani or Sujay. So keep on writing in the chat box. And if you have some really serious doubts, just unmute yourself and talk to me or talk to them. Okay, I'm going to stop now. Any questions? No? I think it's a very simple exercise. So please finish the SDSS one first and then move on to this exercise. I think I will stop sharing. Okay, Indrani?
Yes, ma'am, you can stop sharing now.
Yeah, I'll stop sharing. Okay. And I'll put myself on mute, but I'll be here. So if anyone has any questions, they can always ask me, or they can ask you actually.
No, I think there is one you can answer it. So Vinayak wants to know that convert log of stellar mass to kilogram values or simply use the log values. Okay.
Yes. Simply use the log values. So we want everything in solar mass units. So the dynamical mass will be in solar mass unit. So the stellar mass, gas mass should also be in solar mass units. Everything should be in the units of solar mass, M sun or M dot. Okay, Vinay? Any more questions?
No, not now.
Okay. So you can also, I think Ankit is there also. You can answer the chat box. Okay,
Yeah,
and I'm here.
sure.
Huh? I'm here. Yeah. So Indrani, Sujay, Ankit, after some time, maybe around 4:30, I will just explain the significance of the plots.
Yeah.
Sorry, ma'am.
Okay, okay. Okay. Around 4:30, I'll do that.
Ankit?
Hello.
So although it's going on, is it possible something to display on screen? And
So there is nothing to display actually. The data table is given to them.
okay.
If you want, I can share it again, but it is in the manual. So they have to either write in a table or copy and then plot it.
Okay, because we are doing it on live stream also. So if something like online screen instruction, let it be display on mode.
So
Ankit,
can
I
share the
think
table.
you can display the plots so the students can also compare if they are getting right or not.
Okay, then I can do that.
Okay.
Is it visible?
Yeah, you can, your chat box is visible. You can reduce that. No, now chat box only visible. That's okay. You are sharing the screen. Chat box is visible. It's okay. Close, stop sharing and reshare.
Yes.
Okay.
Now.
Yeah, fine.
Uh,
So what's happening? Are you people getting it? Or if you have any problem, you can always ask. This response.
Maybe at the end, if possible, that plotting program plus the execution can show to the people. Screen sharing through Ankit itself.
Yeah, in the end we can do that.
Yeah, because we cannot expect out of all the people maybe familiar and doing it. At least they'll follow it up at the end.
Yeah, we can share the code also.
Yeah. Ankit, what else you have? I mean, after this, do you have anything?
No, only three things we have to calculate, and then ma'am will explain the physical interpretation of these plots.
Okay. So last 10 minutes, you can save it for your execution itself. How you got arrived this plot and if
Yeah,
possible share screen your window.
yeah, I will show it.
Ankit, Aditya has answered, has asked one question on the chat. Would you like to answer that?
Yeah, I'm answering it.
Maybe you can show it on the screen as well.
So can you see this? So you can use this equation to calculate the dark matter mass.
So if most of the people are done with this, may I request Moushmi ma'am to explain the plots to the students?
Yeah, sure. So, so it was a very simple exercise. I think that most of you would have got it. What I wanted you to learn from this exercise is that the difference of the dynamical mass and the visible mass will give you the dark matter mass in a galaxy. So this is a method that we always use even as professional astronomers. If we have the information about the stellar mass and the molecular gas mass and the neutral hydrogen gas mass, then we can simply, using the relations that I've given you, we can calculate the dark matter mass in a galaxy. Now, the plots, the first plot, the red dots, which is the plot of the fraction of dark matter mass of the dynamical or total mass of a galaxy, plotted against the log of the stellar mass. That plot, actually, I wanted you to plot it to see that the dark matter mass in a galaxy is a fairly high fraction of the total mass of a galaxy. So you can see that it's at least 50% or close to 50% of galaxy masses. Now in the second plot is the plot of the star formation rate against the log of the stellar mass, log m star. So you're basically just plotting two quantities in two columns in the table that I've given you. Now, this is, I think, a very illustrative plot because it shows that as the stellar mass increases, as it increases beyond 10 to the power 9.5, you will see a rapid increase in the star formation rates. This indicates that the more massive galaxies will tend to have more higher star formation. Of course, this is only relevant to disk galaxy or spiral galaxies, not for elliptical galaxies, which don't have any mass in gas. So the most luminous galaxies that you will see are always the most massive spiral galaxies. And so this is a result that actually has become very important because of SDSS. Now we have the stellar masses of a huge number of galaxies. And so we can see this very clearly amongst all the different classes. The last plot, which is the blue dots, is again the star formation rate on the y-axis. But on the x-axis, what is plotted is the ratio of the gas to the total baryonic mass. So the total baryonic mass, m baryon, is nothing but the sum of the stellar mass with the neutral hydrogen MH1 mass plus the m molecular hydrogen mass. Now, whenever you have gas in a galaxy, as I've mentioned in my talk, the gas is the fuel for star formation. So if you have a lot of gas, it means the galaxy has available fuel. So it should form stars. However, what you will see is very surprising. You can see when you plot the blue dots that the galaxies which have large gas mass fractions, those are the ones, the large gas mass fractions are 0.75 or 1. So those galaxies actually have a lower star formation rate. This is actually contrary to what we think. We think that, if a galaxy has more gas mass, it should be producing more stars. But there must be some other underlying physics which prevents a galaxy, even though it has fuel for star formation, from forming stars. And so this is a very important thing which we have to remember. And it's thought that the dark matter halo and the stellar surface density disk, these two things are very important for determining the star formation rate. It's not just the gas mass fraction, which we used to think before. So this is the interpretation of the three plots. And the paper is by Adam Leroy and collaborators. And the quantities they have derived, observed and determined themselves or obtained from archival data. So what you've plotted are mostly real values. Some of the values I had to put by hand because I could not find them in the literature. But in general, the results that you're seeing in these three plots are real results. So you are plotting something which we would also plot as professional astronomers. So are there any questions about the plots?
Yes, ma'am. There is one from Prashad Rathore. So you can unmute and ask Prashad if you are available.
Hello, am I audible?
Yeah. Hello, Prasad.
Yeah, my question was, are the last two graphs like correlated, like star formation rate with respect to the log of mass, and the second
Yeah.
one the fraction? And can we get some sort of useful formulas after interpolating them, like by applying some sort of Gaussian or some kind of interpolation methods?
That's very nice question, very insightful. So the star formation rate depends upon the stellar mass because the more stellar mass a galaxy has, usually it has a higher surface density of stars. And if it has a higher surface density of stars or mass surface density, then you will get more stronger spiral density waves, or you will get global disk instabilities forming. Basically, you will get processes that will cause more and more star formation. Now, when you look on the right, on the blue dots, the galaxies which have more gas fraction actually have less stellar mass. That is not clear from the two plots because, but if you plot it like as a three-dimensional plot, you will be able to find that out. So it's not exactly, you can't exactly correlate the two plots and get this result out. But if you include something else, some other information like the surface density of mass in the galaxies, it will come out. The correlation will come out with stellar surface density.
Thank you, ma'am.
Okay.
Okay. It seems like there is no more question. So
Okay.
thanks, ma'am. It was
Okay, so I will mute myself, but I'll be around. And if Ankit can share his programs, how he plotted, maybe after another 5-10 minutes, that would be really nice.
Yes, sure.
Okay. Okay.
So Ankit, would you like to share the code now?
Yeah, we can ask them if they have
Yeah, if
plotted on.
they need, yes.
I think no one is asking for the plotting. Like I think they are doing.
Okay. So
If they could have faced problem, then we could have shared.
yeah.
Yeah, doing their thing.
Okay, then fine. Hello. Uh, so Crispin, it's 5 already. So can we close or?
Sorry.
So it's
Over.
5 o'clock already. So should we close, ma'am
Yeah.
and service?
Okay.
I'm there actually. We can wait another few minutes maybe if anyone has any questions.
And what about Ankit says he will show the plot and program something.
No, I think no one needs that. Everyone is doing great. So
Okay. Okay.
Yeah.
Fine.
There was one question in the chat with someone asked whether if we need to do a similar calculation for elliptical galaxies, how will we do it? So I just want to mention that for elliptical galaxies, you will be probably have to use the velocity dispersion, which comes from the line width of the galaxy. And then you use the size of the galaxy. Both of these quantities can be put in the virial equation, 2t plus v, to get the mass, the dynamical mass of the galaxy. Okay, I think it's in one of my slides. The slides would have been shared, right, on the site by now? Crispin, is it shared, the slides of the speakers?
No, that part, yeah, it's shared, but I don't know about the this one you are talking about. But
Okay. This is Prasad Rathod. Prasad, did you? I hope you understood how to do it for elliptical galaxies. 2t plus v.
Yeah, I guess we will be taking some sample areas within the same galaxy where where the parameters are put into that.
Yeah. So if you take a spectrum from that galaxy, a very broad spectrum, then you can determine the approximate velocity dispersion of the stars in the galaxy from the absorption line that is seen in the galaxy. From
And for the potential term, like what we'll do, like we need two masses, like interaction between two.
So for this, you will need, just like here, you have dynamical mass minus the baryonic mass. For elliptical galaxies, the baryonic mass will be the stellar mass and the hot gas mass. Okay.
Yeah.
So that's the difference.
Got the answer.
Yeah.
Thank you, ma'am.
Yeah, you're welcome. So I guess, Indrani, if there are no more questions, we can close the session.
Yeah, I think we can.
Yeah. Did Prava say anything about? Did Prava mention anything about keeping it open or anything?
No, I
No.
guess not.
No, once it's over, that's all.
Okay. Okay, so if anyone has questions, they can always write to me or to Vivek or to any of the volunteers, Lavani or Indrani, Ankit or Sujay, and we'll help you. Okay. So I'm going to sign off then. I'll put myself on mute.
Okay, so I would like to both of you, ma'am, and Vivek sir, to make it a great success. Yeah.
So shall we leave also?
Yeah, fine. Yeah, I'll close it. Someone sent in chat, Arvinda. Like you can cross check it. That's it.
He has written only the values.
Okay.
Yeah.
Okay, then. So I'm closing, and please tomorrow the link will be open from 9:10, 9:15 onwards.
Yeah.
You can join. And